In this video, we're gonna prove statements with quantifiers. Let's get on with it. Here's an example to prove a universal statement. Prove that for all m and n natural numbers, if m is odd and n is even, then their sum is odd. Okay, so how do you prove universal statement? Well, to prove universal statement, right, you need to start with assumption that you are taking the objects that you quantify arbitrarily. Okay, so we don't specify what m is, we don't specify what n is, we don't specify which natural numbers they are. We simply just say that m and n are natural numbers, and we're going to use properties of natural numbers when we work with them. Okay, so we start with let m and be, or let's write it in words actually, be two arbitrary natural numbers. Okay, so we start with assuming that we have two arbitrary natural numbers. From this point on, those two natural numbers are fixed. So now we have two natural numbers. One is called m, one is called n. We don't specify what they are, and we're gonna carry on with the proof knowing that m and n are both natural numbers. All right, what are we going to prove after this quantification of m and n? We want to prove an implication, right? We know by now how to prove an implication. We assume the hypothesis, and we show the conclusion. So, assume that m is odd and n is even. Okay, so there exist actually a and b natural numbers such that m is 2 times a plus 1, odd number, and n is equal to 2 times b. Okay, now we check what happened to m plus n. M plus n is 2a plus 1 plus 2b. We can rewrite it the following way, 2 times a plus b plus 1, right? This is the same with the previous expression. And this is an odd number, right? It's 2 times a natural number plus 1, okay, which is an odd number. Okay, and we are done with the proof. Easy peasy, right? So we have shown that for two arbitrary natural numbers, if one of them is odd and the other one is even, then their sum is an odd number. How to prove an existential statement? Let's look at this example. Let A be the set of natural numbers that are even. Show that there exists a natural number n such that n is not a member of A. Okay, so what do we want to prove here? We want to prove, so we want to find n such that n is not a member of A, which means that n is not even. So n is odd, right? So all we need to do here is to find a natural number that is odd, okay? So take, for instance, n equals 3, right? N is a natural number that is not in A. So this kind of proof is sometimes called proof by example, and you should only use proof by example when you prove existential statement. Don't do this for universal statement, because remember, in proving statements with universal quantifiers, we should not specify. We have to select, take the objects arbitrarily. Right, but in this case, right, we can set n to be some natural number that is odd, right, to finish our proof. Okay, so again, to prove existential statement, this is sometimes called proof by example as well. Okay, let's take a look at this example. Prove that the following statement is false. Sometimes this whole thing, proof that the following statement is false, can also be rephrased as disproof the following statement. Yeah, so whenever you see the word disproof the following statement, it means that proof that the statement is false. Okay, so what do we want to prove, disprove here is that for all x in R, if x squared is greater than 1, then x is greater than 1. This is a false statement. Okay, and we're going to prove it. So, to say that the statement is false means what? Means that the negation is true, right? And we know by now how to negate a statement with universal quantifier, right? So the negation, so we want to prove, let me just write proof first. So we want to prove the negation of that statement. What we want to prove is that there exists, right? Remember when we negate a statement with quantifier, for all becomes there exists, such that the statement that is quantified is false. So this, if x squared greater than 1, then x greater than 1 is an implication. Remember what the negation of an implication is. Let me write it in the bottom here. Negation of P implies Q is P and not Q. Yeah? Okay, so such that what? Such that P and not Q, such that x squared is greater than 1, but, well, you can also say n, but typically when we write this, we want to emphasize that the statement is false, right? So we use the connective, replace the connective n by but, which is to emphasize the fact that your statement is false. I made a mistake there, should be its negation. Okay, so let's read it again. We want to prove that the negation of this statement is incorrect. So we negate this the negation of the statement is correct. So we negate this. For all becomes there exists, and this implication becomes false, right? Negation of an implication, P implies Q, is P and not Q. So x squared greater than 1, but x is less than or equal to 1. Okay, so that's what we want to show, right? So now we need to prove an existential statement, right? So what we want to prove here is an existential statement. We need to find an x, a real number x, whose square is greater than 1, but the number itself is less than or equal to 1. Okay, there are many choices. Pick your favorite. Okay, so I'm going to choose x to be negative 2, right? Choose x to be negative 2. We have that negative 2 squared is greater than, which is equal to 4, is greater than 1. But x, which is negative 2, is less than or equal to 1. Okay, and we're done with the proof. Just a quick comment here that when you produce an example to disprove a statement, we sometimes call this counterexample. Okay, so let me write it here. Whoop. Counterexample is an example to disprove a statement, yeah? So it works like an example, but to prove that the statement that you have is false. Okay. Let's take a look at this statement. Show that there is no largest real number. Before we start with the proof, let's think about what we need to show here. There is no largest real number. What does it mean? Intuitively makes sense, right? A real number goes on and on and on and on. But how do we write this statement in such a way that it's easier to deal with? Something that we know all and well. Okay, so let's just do some sketches here, right? To say that there's no largest real number, what do you mean by that? For any, if I take any arbitrary real number, right? Let's call it x. I can always find another real number that is larger than that, right? And every time I do this, if I can do this for any real number, then it means that there's no largest real number, right? That for any arbitrary real number, I can always find another one that is larger than that. Okay, so let's write this mathematically. What we want to show is that for any real number x, there exists another real number such that x is less than y. Okay, so here we want to prove now a statement with universal quantifier followed by an existential quantifier. Okay, so let's now try and apply our experience in the previous two examples and see what we can do here. Right, so for any x in R, so we take an arbitrary real number. Okay, take x, a real number that is arbitrary. Then we're going to find a real number y, may depend on x, such that x is less than y. Okay, can you think of a real number that is greater than x? Again, there are many options. The easiest one to choose is x plus 1, right? So you can choose y to be x plus 1, right? Then we have that x is strictly less than x plus 1, right? Because 1 is strictly less than 0, and then we just translate that inequality, and this is equal to y. Right, so we have shown that x is equal to y. So let's see again the structure. We want to show for any x in R, we let x to be arbitrary. There exists y in R, we choose a real number. Can actually even say that this is a real number, right? And then we show that this property exists. This property holds. Excuse me. Okay. And we show that x is less than x plus 1, which is equal to y, and we are done with the proof. I'm going to close this video with an example of how to prove that something does not exist. Let's read what we are required to prove. Show that there are no positive integers x and y such that x squared minus y squared is equal to 1. So really what we want to show here is that for all x, y positive integer, I'm going to use z plus to shorthand that. For all x and y positive integer, x squared minus y squared equal 1 does not hold. Okay, and how do we proceed from here? Well, we're going to use proof by contradiction, right? The easiest way to prove that something does not exist, assume that it exists, right? And then find a contradiction, okay? So we're going to proceed with a proof by contradiction. So we're going to suppose that what we want to prove is not true, right? So we want to suppose that this is false. So again, assume the negation. Suppose there exists xy positive integer such that the negation of this now, x squared minus y squared equals 1 does not hold. So it means that x squared minus y squared equals 1 indeed holds, right? Now, what I'm going to do is that I'm going to write the following. I'm going to factorize x squared minus y squared as x plus y, x minus y is equal to 1. Okay? And since both x and y are integers, then x plus y is also an integer, and x minus y is also an integer, right? which means that their products, in order for their products to be equal to 1, because these guys are integers, either both of them are 1 or both of them are -1. So now we have two cases. Okay, case 1, x plus y is 1 and x minus y is 1, and we solve if we solve these equations, what do we get? We get that x is equal to 1 and y is equal to 0, which contradicts. It's a contradiction, right? Why? Y cannot be 0. Why is that? Because we assume that both x and y are positive integer. Contradicts y being a positive integer. Okay, so that cannot hold. What about the second case? It's fairly similar. We assume that this guy is -1 and x minus y is also -1. So again, we're solving these and we get that x is -1 and y is 0, which now contradicts the fact that both of them are positive integers. Okay, so the supposition that this whole thing is false is not true. Thus, for all x, y positive integer, x squared minus y squared equals 1 does not hold. Okay, and we are done with the proof. All right, so that's the end of this video. There will be a few more of proof techniques, and in the next one, we're going to talk about the principle of mathematical induction. Thanks for listening.